So how do we interpret everything? So let's look at that previous example. So this would be at 298 Kelvin, and this one would be at 365 Kelvin. Technically, they're both spontaneous processes, but what does it mean when we're comparing them? So the negative sign of delta G indicates that the reaction is not at equilibrium under standard conditions, and that also the Q is less than K. So if the delta G's were equal to each other, then it would be at equilibrium, but they're not. Also, if you had the actual K value and compared it to the Q value you calculated, you'd find that your Q value is lower, and that means that the forward direction is favored, making it a spontaneous process. And then also, the larger the negative value of delta G indicates that the reaction is even farther from equilibrium and favors the forward reaction more strongly. So for this specific reaction, the more temperature, the more spontaneous it became. So when a reaction is at equilibrium, our delta G is equal to 0 and our Q is equal to K. So when these are used in the delta G equation, a bit of rearranging results in a different equation. So if we set delta G equal to 0 and Q equal to K, we can rewrite it to where 0 equals delta G naught at standard conditions plus RT and then natural log of K. So this, remember, this is all at equilibrium. So if I rearrange this equation and I want to get delta G naught by itself, then I will have just subtract RT on ln of K on both sides. That gives me this overall equation. So the standard condition for delta G equals negative RT natural log of K. So remember that T is equal to 298 Kelvin. So here's the relationship of your Gibbs free energy and your K value. So if your Gibbs free energy is less than 0, that makes it spontaneous. And your K value is greater than 1. If your Gibbs free energy is equal to 0, it's at equilibrium. And your K has to be equal to 1 for that also to be at equilibrium. If your Gibbs free energy is greater than 0, it's non-spontaneous. And for that also to happen with K, your K will be less than 1. So to summarize that table, if delta G is less than 0, that's a spontaneous reaction. And then the equilibrium position lies closer to the lower energy products, and K is greater than 1. And then if we start from standard conditions, where at standard conditions Q is equal to 1, the forward process is going to be spontaneous. At delta G equals 0, it's at equilibrium, and then Q is also equal to K. And there's no net change in the forward or reverse reaction. So it wouldn't be spontaneous, it wouldn't be moving either way. And then at delta G is greater than 0, it's a non-spontaneous reaction. The equilibrium position lies closer to the lower energy reactants, and K is less than 1. And then if we start from standard conditions where Q equals 1, then the reverse process is going to be the spontaneous process. But the same thing is if you say the reverse process is spontaneous, the forward process is non-spontaneous. Here's a figure that shows that. We all have the same reaction starting at the same Gibbs free energy. As they approach equilibrium, so equilibrium is K equals 1, which is also equal to Q. What is happening as we have reactants and products? At higher Gibbs free energy, that makes it non-spontaneous, and then at lower Gibbs free energy values, it makes it very spontaneous. So you can see that when K is less than 1, it's going to have a delta G of greater than 0, making it non-spontaneous. And then at K is greater than 1, it means when k's are greater than 1, it means the products are going to be favored. So it's going to be more spontaneous. So delta G is less than 0. And then at delta G equal to 0, that just means that they're going to be the same number once the reaction is done. It's in equilibrium with each other. So what happens if you want to figure out what your equilibrium constant is? Well, we already know that delta G equals negative RT, natural log of K. But what happens if I want to figure out what is K by itself? You just have to rearrange everything. So if I divide negative RT on both sides, I'm left with this equation. But what happens if I want to get rid of the natural log? What do I have to do to get rid of that? Well, you have to take the e to the power on both sides. That gets rid of the natural log. And then I'm left with your equilibrium constant is equal to e to the negative delta G naught over RT. So now we can actually solve for just your equilibrium constant if they give you R, T, and delta G. Here's an example of that. Calculate the equilibrium constant for that same Haber process at 298 Kelvin. So K equals E to the negative delta G naught divided by RT. We actually calculated the delta G already in that previous problem. And we found that delta G naught is equal to negative 32.8 kilojoules per mole. So if you want to know where I got that value, please revisit that previous problem, but that's where I'm getting these numbers from. R is just going to be 0.008314 kilojoules per mole Kelvin. So I just divided by my R constant by 1,000 like we also did on that previous problem. And your T is 298 Kelvin. So if I want to plug everything in, my equilibrium constant is equal to E to the power of negative. And so your delta G is a negative, so don't forget to put it inside brackets, 32.8. And divide that by 8, I converted that to kilojoules, 0.008314. That's kilojoules per mole Kelvin times 298 Kelvin. So those kelvins will cancel, the kilojoules cancel, and the moles also cancel because that's 1 over mole divided by 1 over mole. So that's just going to be 1 over mole times moles. So that's why those cancel out, if you're wondering. So my equilibrium constant for the Haber process is 5.6 times 10 to the 5. And remember that those units all cancel because K and Q are also unitless. Also, if you want to do like this part by itself first and then calculate the E, just in case there's errors, it was just E to the 13.24, and that's how I got this number. Remember, oh, never mind.